Hi. The problem of taking a Boolean vector and leaving only the very first true while all subsequent trues become false is conceptually really simple. And the APL solution to this is also extremely short. The challenge is really to understand how this works. So let's say we have false, false, true, true, false. What we want to do is change the second true into a false because only the first true is going to survive. And the entire APL solution, I'll give you right away, is just these two characters. But why is that? For this, we have to understand what exactly the backslash is doing, which is a scan or a cumulative reduction. And then we have to understand some properties of using less than, which you normally would associate with comparing numbers, but it's being applied here as a Boolean operation. Okay, so first, scan. Scan is actually reductions over the prefixes. So let's say that we take the first three elements of our data. If we also want to take the first four elements of our data, then we would have to take each, and each one of them shouldn't apply to individual elements of our data, but rather to the entire one. So we enclose it to become an entire whole. So here we have the first three and the first four. But we want all the prefixes. We can get the length, and we can get the indices of the length. And so these are all the prefix lengths that we want to take. We compose these two functions together, and then we use them to take each from the entire argument. Okay, so this gets us our prefixes. Let's, for convenience, give this a name. Right. And now we can do a reduction over each one of the prefixes. So this is a less than reduction on each of the prefixes here. And yes, indeed, that gives us the same result because this is the definition of the scan. But why is this? And for that, let's take a bit of a closer look at the properties of less than when used in a Boolean context. So there are only two possibilities for a left argument for less than, 0 and 1, the false and true. And there are only two possibilities of a right argument, 0 and 1, the false and true. Let's do all the combinations. That's an outer product. So we do an outer product, but it's not a multiplication here. It is a less than. It can be a little bit hard to understand what this result represents. So let's decorate it with some headers. I'm going to put the less than character in the corner, and then I'm going to add a header row on top with 3 columns, the 0 and the 1 right next to the symbol. I'm going to put that on top, and then we're going to put a heading for the rows as well, which are also the 0 and the 1s, so they go on the left of this. And now we get a kind of nice table. It's think of it like a multiplication table, but it's a less than table. So 0 less than 0, that's 0. 1 less than 0 is 0. Why? Because it's true and false. So is 1 less than 0? No, it is not. So false, 0. And we can see that there's only one way that less than can give us true. That's this one over here. And it happens exactly when the left argument is 0 and the right argument is 1. So in order to get a final 1 result, we must have a condition where we at all times have 1 on the right, and 0 on the left. Okay, let's go back and look at our prefixes then. So here, we remember that APL reduces from the right, because reduction really means you're inserting the function in all the spaces between the elements. So we start from the right. The first one is just a single element, which just stays the way it is. There's nothing to insert here. Here we get 0 less than 0, which it's not, so it's false, so that's a 0. This is a 1, and here we have 0 less than 1, which is true. So in a sense, this 1 moves over one step. It takes the place of these two elements. And again, we have 0 and 1, and we get a 1. It fulfills the condition. So this prefix, which is the third prefix, results in a 1. And if you look at our data, that's the first one. We get a 1. Now, for the next one, we have 2 1s. So that, according to our table at the end, that gives us false. So the new value, 0, takes the place of these two elements. And we've got 0, 0, 0. 0 less than 0, that's also false. 0 less than 0, it's also false. So the result for this corresponding element, number 4, is false. And over here we have a 0, but again, it's the wrong way. So 1 is not less than 0. That's false. And then that takes a place, a 0 takes place of these two elements. So again, we have 1 and then 0, and that's again false. And then we are back to the same case as we had before, 0, 0, 0, we get false. Another way to think about it is the only way a 1 can survive moving towards the left, towards becoming the end result for this corresponding prefix, is if it has all zeros on its left. If it sees any 1, they will clash and we get 0, and everything is cancelled out from then on. Which means only the very first, the very leftmost 1 can survive. Because the first 1 necessarily has all zeros on its left. And what if there's nothing to its left? Well, that would mean it's the first element. If it would be a 1, then a reduction doesn't do anything, and we just get that 1 back, and so it survives. Any subsequent 1 will hit that first 1 and be cancelled out. There's a lot of talking. Let's try to illustrate this a bit. So I'm going to implement some a little bit involved lambdas or defins, but when we run them, then we'll draw a nice diagram so that we can see what's going on. And all I'm going to do here is I'm going to write covers for the built-in APL. So let's write a cover for the less than function. And we'll start off by printing out what is going on. So we're going to print, and I'll start by printing a little bit of indentation. You'll see in a moment why. Then we print the left argument, followed by the less than to tell that we're actually doing a less than operation. Then the right argument, and then we'll use an arrow to indicate that this gives us a result. And then the result is going to be left argument less than the right argument. So this just prints it. We don't want to return this nicely formatted thing for human consumption. We want to just return alpha less than omega, so left argument less than the right argument. And yeah, we're computing it twice, but performance is not what we're after here. It's just illustration. Okay, then we had the less than reduction that we were applying. Let's define less than reduction. And we're going to do very much the same thing. This time it's one level out, so we're going to give it a little bit less indentation. And then we want to print out that we're doing a less than reduction, and there's just one argument. And then we can print out the result. It's a less than reduction of the argument. And then we'll actually do the less than reduction, but let's use our cover function, because this will have the side effect of printing out every time the reduction invokes the less than function. And finally, we'll write the less than scan in much the same way. This time it's the topmost level, so we don't do any indentation. We'll write out that we're doing a less than scan on the argument, leading to the result of a less than scan of the argument. And now we're going to use our cover for the less than reduction for each. So it would be this, but we instead rewrite less than reduction on each of the prefixes of the argument. Okay, now we can run this. So we did a less than reduction on our argument 00110. And now we're going to do exactly the same thing, but we're going to use our cover function less than scan on this argument. And we get a whole lot of text out. So what is this illustrating? This is illustrating that the overall operation is like a hierarchy. The overall operation is taking this argument here and applying a less than scan to it and getting this result. And as part of that, there were multiple steps. The first step was reducing the first 0. That's the prefix there. And that immediately gave the result. There's no indented line below this because there are no further steps. There's no actual invocation of the function less than. We just directly derive the result without applying anything because there's nothing to reduce. Then we took the next prefix, which were the first 2 zeros, and got the result 0. How did we get the result 0? Well, we inserted the less than between these 2 zeros, which gives us 0. And then we go on to the third prefix that has a 1. And it gives us the result 1 when we do the less than reduction on it. How does this work? Well, we start off with the rightmost 2 elements. 0 less than 1, that gives a 1. And then this one becomes the right argument over here, with the 0 from the left going over here. And with the less than between them, we get a 1. And so this gives us the first 1 in the result that we can see up here, that result there. And then we take the prefix with 4. We start off with the 2 rightmost elements. That gives us a 0 according to our truth table that we computed before for less than. This 0 survives into the right argument of the second invocation of less than with a new 0 on the left. That's this 0. Gives us 0. That goes into here, and we pull down the leading 0. And 0 less than 0 gives 0. And so too, for the last element, we start off with a 0 on the right and a 1 on the left. And then the result, which is a 0, survives into here. We have the same situation, and the 0 propagates on, and eventually we get 0. And so we get the full result, where the first one is the only one that survives, because any other one will clash with that one when it hits it, being reduced from the right. And this is why less than scan is an idiomatic expression for APLers. When dealing with Boolean data, and you need to filter out so that only the first one remains. Once you have some experience with this, then you stop seeing this as a less than reduction, which otherwise will require a lot of reasoning why it exactly gives the result we want, and you just start reading it as a whole as keep the first one. And in fact, there are additional Boolean scans like this that are really useful for performing various operations. But this one is a very famous one. Thank you for watching.